Hello everyone and welcome to our channel Mootechie. It's wonderful to have you here as we dive into a fascinating and fundamental topic in chemistry, the dissociation of water. Get ready to understand the hidden life happening in every drop of water. Let's begin. Our first slide is titled Dissociation of Water with the subtitle Autoionization, K_W and the pH scale. This is our roadmap for today. Now to understand how water splits apart, we first need to understand its structure. This slide shows the water molecule structure, hydrogen oxide. It has a checkmark next to bent molecular geometry. The oxygen atom forms covalent bonds with two hydrogen atoms, and repulsion between lone electron pairs creates this bent shape with a bond angle of approximately 104.5 degrees. Next, we see a point about polarity and dipole moment. Oxygen is highly electronegative, meaning it pulls electrons closer to itself. This makes the oxygen atom partially negative, often written as delta negative, and the hydrogens partially positive, or delta positive. This leads us to hydrogen bonding. The polarity allows weak hydrogen bonds to form between water molecules, which is what gives water its unique properties like cohesion and a high boiling point. A key concept box reminds us, this polarity is the fundamental reason why water can autoionize and act as a universal solvent. It's the heart of the matter. And we have little labels confirming the partially negative oxygen and the partially positive hydrogens. Now let's translate this structure into chemical action. This slide is all about chemical equations. First, we have the simplified notation. Historically, this was written as a simple dissociation, hydrogen oxide in equilibrium with H and OH. But the accurate molecular view is even more interesting. In reality, protons or H do not exist freely in water. They instantly bind to another water molecule to form what's called a hydronium ion. So the accurate equation is two hydrogen oxide molecules in equilibrium with hydrogen oxide, hydronium, and OH, hydroxide. This brings us to the idea of dynamic equilibrium. The double arrow indicates the reaction is reversible and reaches a state where the rates of the forward and reverse reactions are equal. It's a constant dynamic dance. A very important note here. In most chemistry contexts, the concentration of H and hydrogen oxide are used interchangeably to represent acidity. So if you see H, just think hydronium ion. The slide also has a heading for proton transfer process, which sets us up perfectly for the next concept. So what is the result of this constant proton transfer? Let's explore the ion product of water, Kw. This is defined as the equilibrium constant. The ion product constant, K_Wi, represents the product of the molar concentrations of hydronium and hydroxide ions. That's written as K_W equals the concentration of hydrogen oxide times the concentration of OH. Now, the value at 25 degrees Celsius is crucial. At standard room temperature, 25 degrees Celsius, K_W is experimentally determined to be a very small number, 1.0 times 10 to the power of -14. This leads to neutrality in pure water. Since the ions are produced in a perfect 1:1 ratio, the concentration of hydronium equals the concentration of hydroxide, and both are equal to 1.0 times 10 to the power of -7 molar. But it's not always constant. There's temperature dependence. K_W varies with temperature. As temperature increases, the dissociation reaction increases because it's endothermic, which means it absorbs heat. This causes K_W itself to increase. The slide also labels the two key molecular species involved, the hydronium ion and the hydroxide ion. This process has a special name. Let's define it clearly. So what is dissociation or autoionization? It's a proton transfer process. Autoionization involves a proton, H, transferring from one water molecule to another. One water molecule acts as an acid, the proton donor, and the other acts as a base, the proton acceptor. This is how we get the formation of ions. This reaction produces a hydronium ion and a hydroxide ion. I want to emphasize, it is not a simple splitting of a water molecule. It's a genuine chemical reaction between two molecules. And it exists in a dynamic equilibrium. The process is reversible and occurs spontaneously, but to a very small extent. In pure water, molecules are constantly ionizing and recombining. Here's a mind-blowing note. Even in what we call pure water, these ions are always present, though in extremely low concentrations. To be precise, only about 1 in 550 million water molecules is ionized at any given moment. The slide has a diagram illustrating this, showing two water molecules with an H transfer between them forming hydronium and hydroxide. Now, how do we measure this? With a famous scale you've probably heard of. Let's talk about the pH scale and dissociation. First, the logarithmic scale. pH measures the concentration of hydronium ions using this formula. pH equals negative log of the hydrogen oxide concentration. Similarly, pOH equals negative log of the OH concentration. Because of our friend K_W, where the product of hydrogen oxide and OH is always constant, we get a simple relationship to K_W. If we take the negative log of both sides of the K_W equation, we get a wonderfully simple sum rule at 25 degrees Celsius. pH plus pOH equals 14.00. This leads to a crucial point about neutrality and temperature. Neutral means the concentration of hydronium equals the concentration of hydroxide. At 25 degrees Celsius, this happens at pH 7. However, as temperature increases, K_W increases, which shifts the neutral pH to lower values. For example, at 100 degrees Celsius, neutral pH is about 6.1. This is so important, let's read the crucial note aloud. A pH of 6.5 can be neutral if the water is hot. Neutrality is defined by the balance of ions, not just the number 7. Remember that. Now the slide has a fantastic pH scale chart. On the left we have increasing acidity, where hydronium concentration is greater than hydroxide. It lists common substances. For instance, at 0 we have battery acid, at 1 is lemon juice, at 2 is vinegar, and it continues up to 14. On the right we have increasing basicity, where the hydronium concentration is less than hydroxide. So what can change this delicate balance? Let's examine the factors affecting dissociation. The first and primary factor is temperature. The dissociation reaction is endothermic. So increasing temperature shifts the equilibrium to the right, following Le Chatelier's principle, which significantly increases the value of K_W. Next are pressure effects. While minor under standard conditions, very high pressure, like in deep oceans or supercritical water, promotes ionization because the ions actually occupy less volume than the neutral water molecules. Finally, there are other influences like high ionic strength from salt concentrations and strong electric fields, which can alter the activity of water molecules and affect dissociation rates. There's another crucial note here that reinforces our earlier point. At 100 degrees Celsius, K_W is 51.3 times 10 to the minus 14. This means pure water has a pH of about 6.1, but it is still neutral because the concentrations of hydronium and hydroxide are equal. The slide includes a graph titled, Effect of Temperature on K_W. It shows a curve that starts very low at 0 degrees Celsius and rises steeply as the temperature increases to 100 degrees Celsius, visually demonstrating how the ion product constant grows with heat. Why does all this matter in the real world? Here are the applications, and this is why it matters. A. Acid-base equilibria and buffers. The value of K_W is absolutely fundamental for calculating pH in weak acid and base solutions, and for designing buffers, which are crucial for chemical stability in so many processes. B. Biochemistry and life. Enzyme activity in your body depends strictly on pH. Cellular homeostasis relies on water's dissociation to maintain proton gradients, which are essential for energy production. C. Environmental chemistry. This process controls the solubility of minerals and heavy metals and directly impacts the health of aquatic ecosystems, a key factor in issues like ocean acidification. D. Electrochemistry and corrosion. Water dissociation participates in redox reactions, influencing everything from battery efficiency to the rates at which metals corrode. The slide also lists biochemistry, analytical labs, and the chemical industry as key areas where this knowledge is applied. So let's bring it all together. In conclusion, here is a summary of key concepts. Dynamic equilibrium. Water naturally dissociates into hydronium and hydroxide ions in a reversible process. Ion product constant, Kw. At 25 degrees Celsius, this equilibrium constant is fixed at 1.0 times 10 to the negative 14. The pH scale. This scale is derived directly from the hydronium ion concentration with pH equals negative log of hydrogen oxide. Environmental factors. Dissociation is endothermic, so increased temperature leads to a higher K_W. And finally, this process is the foundation of chemistry. It underpins all aqueous acid-base chemistry and is vital for biological pH balance. Thank you. See you in the next class.